Before we go to our lesson, let's consider first this graph of the function y is equal to f of x. From calculus of single variable, we observe that the function has a relative maximum at x is equal to c, meaning there is a region in the graph such that f of c is the highest value of f. Similarly, f also has a relative maximum at x is equal to e. Another observation is that there is a relative minimum at x is equal to d. So in this small area of the graph, f of d is the lowest value of f. Just to emphasize which are not considered as relative extrema, let's also write here that f has no relative extremum at x is equal to a, b, and f. To be a relative extremum point, the function must have values around that point. Thus, the function cannot have any relative extremum at x is equal to a, nor at x is equal to f, since these are the endpoints of the graph. And at x is equal to b, f cannot have a relative extrema because f of b is not defined. Candidates for relative extrema must be in the domain of f. Before we define the relative maximum and minimum of functions in two variables, let's recall the definition in single variable. Let's take a point x0 in the domain of f. We say that f has a relative maximum at x0 if f of x0 is greater than or equal to f of x for all other values of x in some interval containing x0. To illustrate, f has a relative maximum at this x0 if there is some open interval that encloses this x0 such that the value of x0 under f is greater than or equal to the function values of other x in this interval. Now for functions of two variables, there are few logical changes from this definition. First is instead of x0, suppose we have an ordered pair or a point x0, y0 in the domain of f. We say that f has a relative maximum at that point if its value under f is greater than or equal to the other f of x, y for all points in some disk containing x0, y0. So for some area on the plane around x0, y0, f of x0, y0 is the highest value. Now let us define the relative minimum of f of x, y. It's almost the same, but we will change the word maximum and the inequality greater than to minimum and less than or equal to. Thus, if f has a relative minimum at a point, that means f is lowest at that point for some local area around that point. Now, if f has a relative maximum or relative minimum at the point x0, y0, then we say f has a relative extremum at that point. Relative extrema for the plural. Although the definitions are quite easy to grasp geometrically, it is difficult to find the relative extrema analytically if we use these definitions. Instead, we use the critical points and second derivative test. So let's go back first again in usual function f of x. Recall that we have a theorem stating that if f has a relative extremum at x is equal to c, then the derivative of f at c is 0 or undefined. Now, is the converse of this result true? Not necessarily. If the derivative of f at c is 0 or undefined, then possibly f has a relative extrema at x is equal to c, but we are not sure, thus we only call them critical numbers or critical points of f. This concept is analogous for the function f of x, y. If f has a relative extremum at x0, y0, then the two partial derivatives f sub x and f sub y are 0, or at least one of these derivatives does not exist. Similarly, the converse of this is not necessarily true. If the derivatives are 0 or one of them does not exist, then we say that f has a critical point at x0, y0, given of course that this point belongs in the domain of f. Before we continue to the second derivative test, let us answer this example. Find all the critical points of x squared minus y squared. The given function is a polynomial function. Thus, it is continuous everywhere on r squared, and that implies the partial derivatives exist at any point. So in the definition of the critical point, we don't have to bother thinking about this part, since there is no point that makes f sub x nor f sub y non-existing. These derivatives always exist. Thus, to find critical points, we only need to check when is f sub x and f sub y both 0. So let us solve this system. First, what is f sub x? Treating y as a constant, as a fixed real number, then the derivative is 2x. On the other hand, f sub y is negative 2x. If we divide both sides of f sub x by 2 and f sub y by negative 2, then we obtain x and y are both 0. Therefore, the point 0, 0 is the only critical point of f. Now let us recall this remark that if a point is a critical point, it does not follow that there is already a relative extrema at that point. We give such points particular name. All critical points of f that are not relative extrema are called saddle points of f. Later, we will see those saddle points on the conclusion of the second derivatives test. But first, let us recall SDT for a function f in terms of one variable x. Suppose we have a critical point at x is equal to c, and the second derivative of f at c exists. If that second derivative is positive, then f has a relative minimum at c. On the other hand, if the second derivative is negative, then f has a relative maximum at c. If the second derivative at c is 0, then there is no conclusion. For this special case, we need to find other ways, maybe first derivative test or observing the graph of the function to determine if there is a relative extrema at c or not. Now let's compare this to the second derivatives test for f of x, y. Let x naught, y naught be a critical point of f. Suppose the four second order partial derivatives f sub xx, yy, xy, and yx are continuous on some disk which contains the critical point. So here the derivatives do not only have to exist at that point, but must be continuous in particular. That means the derivatives exist and are equal to their limits. Before we go to the conditions, let us define D to be the product of f sub xx and yy minus the square of f sub xy, where each derivatives are evaluated at the critical point x naught, y naught. Now, if D is positive and f sub xx is also positive, then f has a relative minimum at the critical point x naught, y naught. If D is positive yet f sub xx is negative, then f has a relative maximum at x naught, y naught. Now, if D is negative, then f has a saddle point at x naught, y naught. That is, we are sure that there is no relative extremum at that point. And if D is 0, then there is no conclusion. That is, there may or may not be a relative extrema at the critical point. So for this special case, oftentimes we observe the nature of the function carefully, possibly together with its graph to determine if there is a relative extremum, but for our class, we will only consider functions where SDT would apply. Maybe you are wondering, why is the derivative f sub yx not included in D? We have a result that if a function is continuous on some disk or a circular region, then f sub xy is equal to f sub yx for all points on that disk. That is why this condition is necessary. So the square of f sub xy here is actually the product of f sub xy and f sub yx. We will not bother discussing the proof of this second derivatives test. What we wish to do here is how to apply this test. So we have the following steps in finding the relative extrema using the second derivative test. First is we solve the system of equations when f sub x and f sub y are both 0. These points are the critical points of f. Next is compute for the second order partial derivatives f sub xx, f sub yy, and f sub xy. Next step is to compute d for each point we obtain in step 1. And from there, we use the second derivatives test. As an example, let us find the relative extrema and saddle points of 8 minus 3y squared minus 6xy minus 2x cubed. First, let us solve this system of equations. What is f sub x? If we treat y as a constant, then the derivative is negative 6y minus 6x squared. For f sub y, let us treat x as a constant, so we have negative 6y minus 6x. Let us simplify this first, divide both equations by negative 6, and isolate y on the left side. Both expressions on the right side are equal to y, so we can equate them like this. Please be reminded that we cannot cancel x here, for we do not know if x is 0 or not. Instead, we transpose x squared to the left side, then factor out x. This gives us either x is 0 or x is 1. Now we have these functions for y. We can use any of these two to solve for the corresponding y value. If x is 0, then y is also 0. And if x is 1, then y is negative 1. Therefore, our critical points are 0, 0 and 1, negative 1. Our second step is to solve for the second order partial derivatives given this f sub x and f sub y. The derivative of f sub x with respect to x is negative 12x. The derivative of f sub y with respect to y is the constant negative 6. Lastly, the derivative of f sub x with respect to y is also negative 6. For the third step, we compute d for each critical point. So let's fill in this table. Let's evaluate f sub xx, that is negative 12x, on the first point 0, 0. X is 0 here, so negative 12x is also 0. For the second point, x is 1, so negative 12x is equal to negative 12. And for f sub yy, we have a constant, so there is nothing to evaluate here. We can write immediately negative 6 on both rows. The next derivative is also constant, but let's get its square to help us compute d faster. So let's write here positive 36. Now to compute d, we multiply 0 and negative 6, so that is 0, then subtract 36, so we get negative 36. Similarly, for the second point, negative 12 times negative 6 is positive 72 minus 36, so we write positive 36. Then let us use s dt. For the first point, d is negative, so we get a saddle point. For the second one, d is positive, and f sub xx is negative, so we have a relative maximum. Therefore, our conclusion is f has a saddle point at the origin and a relative maximum at 1, negative 1. For our last example, consider x cubed minus 3x squared plus y squared plus 2y minus 5. Let us solve this system of equations. I leave it to you to verify that f sub x is 3x squared minus 6xy and f sub y is negative 3x squared plus 2y plus 2. Simplify the first equation by dividing 3 on both sides. For the second equation, let us isolate y on the left side, then substitute this y value on the first equation. We can distribute negative 2x, so we have this. And just to make our equation nicer to look at, multiply both sides by negative 1 and arrange the terms by decreasing order. All terms have x, so let's factor out x. Then factor the second term as the product of 3x plus 2 and x minus 1. And so the values of x are 0, negative 2/3, or 1. Let us use this to solve for the corresponding y values. This is arithmetic and I leave it to you to check that this will be the values when you plug in the x's. Thus, our critical points are 0, negative 1, negative 2/3, negative 1/3, and 1, 1/2. Now, given this f sub x and f sub y, we obtain the second order derivatives. So f sub xx is 6x minus 6y. F sub yy is only the constant 2. And f sub xy is negative 6x. Let us evaluate these derivatives on our three critical points. For 0, negative 1, 6x minus 6y is positive 6. For the next one, please do check that it is negative 2. And for 1, 1/2, we have positive 3. The next column is constant, so there is nothing to evaluate. And for the last one, we square negative 6x, so we have 0, 16, and 36. Next, we compute d. 6 times 2 minus 0 is 12. Negative 2 times 2, that is negative 4. Then minus 16, so we have negative 20. Lastly, 3 times 2, we have 6. Minus 36, so negative 30. For the first point, d and f sub xx are both positive, so we have a relative minimum. The other two have negative values for d, so surely that's a saddle point. Thus, we conclude that f has a relative minimum at 0, negative 1, and a saddle point at negative 2/3, negative 1/3, and 1, 1/2. Please try answering the following exercises.